Um, so we actually moved on to projected gradient descent and constraint optimization. Um, and this was basically foraying from our discussion on generalized act. Not starting up. You can hear me, right? Listen, very good. So we were discussing how projected gradient descent is a specific instance of constraint optimization. So here's the big picture with generalized gradient descent. We had the Cx. The Cx could be basically an indicator function coming from constraints, and we have a general claim. The claim is that if fx is convex differentiable, if f is Lipschitz smooth, and Cx is convex, and this prox, right, prox can be computed exactly, then the convergence proof is very similar to that of gradient descent, ordinary gradient descent, under similar conditions. I mean, Lipschitz smoothness, etc. So this is a very good result, and if we have projected gradient descent where we have constraints, we are able to leverage this good result, fortunately, right? And additionally, now because we have related all this to gradient descent, we can also leverage acceleration. The z that you'll get in the proc step could be obtained using acceleration. So you basically project onto an accelerated step, you do a prox on an accelerated step, and so on. Right? Now you may ask, okay, what if I had I know that Cx is not differentiable, so let me have applied subgradient descent, right? I could have done subgradient on C fx plus Cx, okay? But the problem is for subgradient descent, you can't do better than order of 1 upon square root t. Right? So that's not what we are getting here. So that's a clear advantage we have got. Better convergence because of assuming differentiability of f, Lipschitz continuity of gradient, and obviously now you can use accelerated. Now accelerated for subgradient is not known. What does it mean to keep accumulating gradients, right? The momentum part across time for subgradients again doesn't make sense. Okay, so this has been a big breakthrough, by the way. Oh. Now, if you add acceleration, you'll actually get 1 upon t square. Error will shrink as 1 upon t square, which is even better. Empirically, right? How does it look like? So this is very interesting as one representative plot. Subgradient method would have been here. Okay, that's pretty bad for fx plus cx. Moment you apply generalized gradient descent, which is using the prox operator, you're like way better, a big gain. And moment you apply acceleration, any momentum based advancement, again you see a huge gain. Okay, this kind of sums up the story of accelerated gradient descent, accelerated generalized gradient descent. What I have in these slides, I mean, if you really are liking proofs, this is probably the most complex set of convergence proofs for accelerated generalized gradient descent. I won't get into the details. There's a lot of notation here, but I think this is a result. What I prove is this one, right? Where I've assumed that the prox step can be computed exactly. That is an assumption being made here. Okay, obviously it requires you to uh, look at the fact that you may have the prox will involve an intermediate step, which is the unconstrained update. So there's a lot of kind of math required here, uh, and that's the end of this part. Now I'm going to focus a little bit more on this projected gradient descent case. Okay, uh, how would you solve the prox operator in general for projected gradient descent? We did this for proximal, but I will now come up with some calculus for projected as well, some examples for projected. Okay, so one important point before we move there, in terms of convergence, uh, so far we assume that the prox operator can be computed exactly. But what if I can't do it exactly? So in this work, inexact proximal gradient methods, they they are able to derive some healthy conversion rates if the errors due to the approximation can be controlled. Okay, uh, if we can avoid multiplicative or cascading errors, right? That control is there, then um, we can be doing well. Okay. Otherwise, there's nothing more I want to present here. Well, now let's look at projected gradient descent, which is very special case. This is a nice image to carry in mind. What are we doing here? So we're saying that after you compute your IT plus one update, you're doing projection. Let's say this is our constraint set, right? And these are the level curves for F. Okay. So these are level curves for F. Of course, they pass through this constraint set as well. And this is my C constraint. So the natural idea would be if I am, say, at a point here, I want to project through an orthogonal projection, right? No notion of projection to you generally would mean an orthogonal projection. If I was here, I moved in this direction, right? I was here, I moved in this direction, I would go back here. This is a picture to carry in mind. Question is, how do you solve it exactly? Well, if you can define PCX is argument over all the possible y's in the constraint set of x minus y norm square, then you would have projected. And this is pretty much what prox should give, right? You remember the prox operator was doing this. This is what prox will give. Okay. So this is an update. The min over x and c of f of x can be written as computing xt plus 1 using your gradient descent or favorite accelerated gradient descent, and then sorry yt plus 1, and then use this yt plus 1 to project on xt plus 1 using this projection operator. Okay, I've kind of depicted all of this on the slide as well. Xt here is yt plus 1, and then you go back to xt plus 1. Okay, so again, I'm just highlighting the connection between the proximal and projected gradient descent. Its projected gradient descent is simply an instance of the proximal gradient descent. The proxy is the this projection operator is the prox operator under constraints. Okay. The way you have obtained it is by setting the C function. You just set up the C to the indicator function. The C is actually the indicator function. If you want, you can write it more formally as fx plus icx. That's how you obtained your projection. Okay. Now the tools for getting this projection are KKT conditions, Lagrange duality, and so on, right? Which we'll cover in as many classes as possible, but very briefly again. Okay, so this is overall projected gradient descent. You look at the unconstrained update, and then you project to get the constrained update. So what we are going to look at is ways of solving this. Okay, so this is going to be a very important picture for us to carry in mind. Now what we'll do is to help facilitate the computation of the projection, we'll look at the level curves of the function. This is f, and think of now I've used g instead of c. Okay, the same thing. I have a constraint here, g1 x less than 0. I have only one constraint. Okay, so level curves, and as you can see, as I move in this direction, right, the function values are increasing for f. And as I move in this direction, I am entering the region of G1x less than 0. I want to minimize f, which means there's a tension. I want to minimize f and yet honor the constraint G1x less than 0. Okay. A simple constraint G1x less than 0. We'll look at more complex later on. Okay. And in fact, I've taken it to be Gx less than equal to C, but without loss of generality, set C to 0. Okay. So this is the exact projection step. So how do we solve for this? We solve for this by defining what I said is a Lagrange function. Okay. So we're going to kind of conclude with this slide today. So now what is my problem? My problem is this G1x less than 0. We'll look at how this magical Lagrange function comes from a duality theory perspective later on. But I'm defining my new Lagrange function. Very much inspired by kind of the prox. So this new Lagrange function is basically the projection function 1/2 norm of z minus x, because I'm trying to solve the projection function. I'm trying to do the projection, right? And what have I done? I've added a lambda times gx minus c. The c can be 0. So if I take the optimality conditions of on this Lagrange function, let's say I want to minimize it. The gradient with respect to z should be 0. And the gradient with respect to lambda should be 0. Okay. Yeah. So what are the options here? Okay. A little bit of animation might help. So what are the options here? Either x is in C. Okay. Either x is within the constraint set in the interior, and the constraints are not active. When I say constraints are not active, I mean G1x is strictly less than 0. If active constraint means G1x is equal to 0. Okay. So in this region, this is inactive constraint. Inactive. G1x strictly less than 0. This is a region where G1x is exactly equal to 0. Now, very intuitively, if I move within the set, right? If I move here, I'm going. In this case, I'm going to increase the value of the function. So there's a tension, as was pointed out earlier. So if the optimal point happens to be on the boundary, then what should I have? What should happen? It means we could not decrease the value of g further while also decreasing f. If it's on boundary means if I have to decrease g, I'll end up increasing f. So gradients of g and f must be in opposite directions, right? If optimal point is on the boundary, so that is a part in pink. If x is on the boundary, g is now if you take the derivative gz equal to c, and z minus x plus lambda times gradient of gz is 0, which means z minus x and the gradient of gz are in opposite directions. That so I'm connecting the interpretation with respect to the figure and the derivative of Lagrangian going to 0, right? In the case of x being on the boundary, if the optimal point was on the boundary, that is that's point 2. Point 1 is simple. If x is within the set, in which case what happens? Gz is less than c, and all we need is that the gradient of L with respect to z should be 0. As if the constraints did not exist, right? The constraint did not exist. That is z equal to x. There's no project, and basically there's no projection. Projection means you're on the boundary. Otherwise, there's no projection. Everything is right. Status quo. So I have some optional course material where I in my previous offerings of the course I would spend a lot of time explaining this figure, but I think this is good enough to help solve. So what I want to do is leave you with a homework problem here. So try computing the projection operation for these functions. Okay, so gx, let's say A transpose x is less than C. That is my, so A transpose x is less than C is my constraint. How will I do the projection? Or norm x square is less than C, right? So if you just apply the Lagrange constraint, write down the Lagrange function, apply the constraint, you'll get A transpose x is equal to C, which is on the boundary. If A transpose x is on the C, this is on boundary, and Z minus x and A are in opposite directions. What is A? A is the gradient of A transpose x, right? If it's on the boundary. If it's not on the boundary, then Z must be equal to x. There's no projection. The prox operator is vacuous, just no projection. Okay. So what is this? So you try out these simple, very simple cases. Okay. So for each of the example constraints, apply the necessary condition for constraint optimality and try and derive the projection operation. Is that fine? And just to kind of give you an idea, uh, so this is a kind of all projection, several important projection operations you can see. Intuitively, you'll find them very easy to understand. Projection literally is just projecting. How do you derive these is the question. So derivation requires you to set the gradient of L to 0. Is that clear? So let's try and apply. Any question? So I'm going to leave you with this homework problem. For all of these, try and derive the projection operator. Any questions? Thanks. We'll conclude for today.